Okay. Okay. Good morning, everyone. Today, I'm very glad to present Professor Kasso Okoudjou. I hope I pronounced that correctly.
Yes.
From Tufts University in Boston, in the U.S. Professor Kasso is an expert in harmonic analysis. He studied both pure and applied numerical harmonic analysis. He also studied analysis and differential equations on fractals. And he got his PhD from Georgia Tech, and also has held positions at several universities over the world. For instance, he has been at MIT, he's been at University of Maryland, in the Technical University of Berlin, Germany, in Cornell University, and some others. So we are very glad to have you here, Professor. He will speak about orthogonal polynomials in fractals, which of course is the topic that we this is similar for this topic. So thank you for accepting the invitation, Professor, and you can start anytime.
Thank you very much, Luis, for the kind invitation. And because I cannot see anyone, if you have a question, please unmute yourself or put it in the chat, and Luis can read out the question.
Okay.
Thank you. I'd like to talk to you about a theory of polynomial, and especially orthogonal polynomial on fractal. And the main example of fractal that I'll look at later is going to be the Sierpinski gasket. So before I start, some of my collaborators over the year on this project are listed here. I got introduced to this whole area of math by Robert Strikas, who sadly passed away about 2 years ago. I was his postdoc at Cornell. That's how I started learning about analysis on fractal, and we wrote a paper on polynomial on the Sierpinski gasket. And many of these sort of what I'm doing now can be traced back to what Strikas and we did at that time. So at the time, there was a student who was an undergraduate student at the University of Maryland, Caitlin Tuley-Hood. So she worked on this project with us during the summer. So that's how we sort of got started. And since then, we've sort of expanded the number of people working on this project. So for this group, I feel like I shouldn't sort of do much about a review of the theory of classical orthogonal polynomial, but I do want to sort of set the stage for some of the things that I would like to present. So the first part of my presentation, which is sort of roughly divided in 3 parts, it's going to review quickly some of the fundamental of polynomial, classical polynomial, Legendre polynomial, for instance. And then I'm going to spend some time sort of setting the stage for what we know today as analysis on fractal, especially the Sierpinski gasket. So I'll sort of briefly describe the main tool that are needed, and then I'll spend some time talking about the theory of polynomial in themselves. Now, once you have a polynomial, if you have an inner product space, then it's not so difficult to sort of construct a family of orthogonal polynomial by just going through the Gram-Schmidt process. And that's what the last part of the talk will be about. My hope is, if all goes well, I'll go through definitely the Legendre orthogonal polynomial. Once you have orthogonal polynomial, you can sort of associate them naturally with a class of 3 diagonal Jacobi matrices, and there is a one-to-one correspondence between like the spectral measure and this Jacobi matrix. So I'll try to sort of show that for this, even in this fractal setting, we do have the same thing. And if we have time, I'll talk about orthogonal polynomial on the Sierpinski gasket, especially the Sobolev kind. So where we change the inner product to get like a new set of polynomial. All right. So the classical Legendre polynomial, the way I like to sort of think about them is from a least square approximation point of view. I mean, my background is in harmonic analysis, so I like to sort of approximate things a lot. So if you give me a function in L2 and I try to sort of find the best polynomial of degree at most n, that sort of is closest to the function in the L2 sense, then you naturally realize that the solution are given by the projection of your original function onto this orthogonal polynomial that are called the Legendre polynomial. So that's one way to introduce them. This is a pretty classical problem. You just write a polynomial here, you multiply out, you sort of realize that to minimize this, you just have to sort of take this projection with respect to this orthogonal polynomial. So there is nothing new in here. To be more specific, the way you can construct the Legendre polynomial, orthogonal polynomial, you take like the monomial t to the power k, and then you just orthogonalize them with respect to, here I'm just taking the standard Lebesgue measure on -1, 1. And you get a family of orthogonal polynomial that don't have L2 norm 1. And then if you normalize this, you get the orthogonal of the orthonormal Legendre polynomial. So the good thing about this is that the highest the coefficient of the highest order is 1. So that's why we call them a monic orthogonal polynomial. And so I want you to keep this in mind because I would like to sort of do something analogous on the Sierpinski-Gasquet. One of the fundamental relations in the theory of orthogonal polynomial is the three-term recursion formula, which is written here. And a good way for me to think about it is actually to sort of, so if I were to sort of think about this is, okay, what I'll do, because I'm using the iPad, I can just add like a quick sheet here, add a page, and I'm going to move this back here. So, okay, so oh, I thought, yes, this is a page that I just added. So a good way to do it is just to look at the polynomial t multiplied by pi tilde k of t. This is a polynomial of degree k plus 1. And because you know you can expand it into an orthonormal basis, you just write t pi tilde k of t as maybe some alpha pi tilde k plus 1 plus beta pi tilde k plus gamma pi tilde k minus 1 plus, sorry, I think I'll just stop here and I'll just write plus lower order. And the nice thing is if you compute the inner product of this with all the lower order, you get 0. So you know there is no lower order. And this gives you exactly the three-term recursion formula that I just wrote over here. So that's essentially how you get the three-term recursion formula. And the key thing I want you to remember, because we're going to come back to that, is that in order to get a polynomial of a degree 1 higher than what you have, you do it by multiplying by just the monomial t. And that's something that we're going to try to sort of mimic on the Sierpinski-Gasquet. So I'll come back to this when we get there, but you all know this relation, you all know how to prove it, so I shouldn't sort of spend too much time on it. And the final thing I would like to do is you can record like the three-term recursion formula in this matrix that's called the Jacobi matrix. And the spectral measure that associated to this is exactly what we have in this particular case. It's just a Lebesgue measure on -1, 1. So my goal is to try to do all of these on a fractal set. So for me, a fractal is, I mean, the best definition I've seen of a fractal is that I know one when I see one. So the easiest one that I like to work with is the Sierpinski-Gasquet. And a way to look at it is through the theory of iterated function system. So this is an example of an iterated function system. I take a free contraction of a plane. So fi of x is just like the contraction of ratio 1/2 that fix 3 points in the plane. Usually the way you'll do it, you'll start from an equilateral triangle where the vertices of your equilateral triangle are q0, q1, q2. And then you apply this map to it, and then it's just going to generate the Sierpinski-Gasquet in a minute. I'll show the picture in a few minutes. So the Sierpinski-Gasquet is actually the unique non-empty compact subset of R2 that satisfies this self-similar equation. So you can write it as a union of small piece of itself, that's the self-similarity part. And you can actually do this more generally, like you call a word of length omega to be like, so here omega is just like omega 1, omega 2, all the way to maybe omega k. And when I said the word omega m, this is a word of omega of length m, and each of the omega I belong to 0, 1, 2. And so what you're seeing here, f omega, is nothing but f omega m composed with f omega m minus 1 composed with, all the way to composed with f omega 1. And that's just a composition. So I can sort of compose this many times. And if I sort of collect all the word of a given length and I take the union of all of those decomposition, I'm going to get, again, the Sierpinski gasket. So picture are better to sort of capture this. So this is an approximation to the Sierpinski gasket. So I start from an equilateral triangle of vertices Q0, Q1, and Q2. I apply these 3 iterations. So what happens is when I apply the first one, I sort of just reduce my whole thing to this upper triangle. When I apply a second time, I reduce it to this. And then when I apply to a third time, I reduce to this. And then I iterate this process over and over again. And in the limit, what I get is just called the Sierpinski gasket. So a good way to actually look, a good way to look at this is to view the Sierpinski gasket as a limit of a sequence of graph. And this is a graph that I'm describing here. So this is a graph V0. The vertex of the graph are your 3-point V0, Q1, Q0, and Q2. And then you sort of put the edge on them. And then what you do next is just you apply your 3 iteration. When you apply your 3 iteration, this point is fixed by the first one, but then the 2 points that are at the bottom are brought to this location. And then when you apply the second iteration, your second contraction, you get like this one is fixed, and these 2 are brought into this position. And then the last one will fix this point and will bring this one here. So what you've done is you start from a graph that has only 3 vertices, and then you add essentially 3 new vertices. And then you repeat this process. So this is after step 1. This is applying the same thing for step 5. And this is after 10 steps. After 10 steps, you can't sort of see the point in the graph anymore. This is really converging very fast to actually the fractal. That's called the Sierpinski gasket. So that's sort of the geometric construction of a gasket. But what I care about here is actually the analytical structure on the gasket. So the first thing I would like to do, and that's going to be the basis of everything I'm going to talk about, is to define a Laplacian, or now the Sierpinski gasket. So the Laplacian is going to be defined as a weighted limit of graph Laplacian. Graph Laplacian are easy to describe, right? Because if you look at this graph V1, then every point except for V3, so why don't I use a different color to sort of highlight those? So everything, so I'll put this point in black now. This, and this have exactly 4 neighbors, right? This is neighbor 1, neighbor 2, neighbor 3, and neighbor 4. And then if I go to any level, even if I were to pick this point, and then if you look closely, at this level is the big triangle that here. So if I look at this level, the neighbor of this point are just this one, this one, this one, and this one. So every point except the original 3 points that I start from Q0, Q1 will have exactly 4 neighbors. So to define a Laplacian on this graph, all I'm going to do is I'm going to say at a given level, my Laplacian is going to be defined by, let me change color quickly. So my Laplacian is going to be defined at a level M by looking at the sum over all the neighbor to my point, and then I'm just going to sort of take out how many point I have as a neighbor for each one of them. So everything has exactly 4 neighbors except for these Q0, Q1, and Q2. And so this is going to be a very well-defined Laplacian on the graph. It's a local operator. And the key thing is actually, it's not trivial to figure out like the correct weight that one must sort of put, or the correct sort of ratio that one must put in front of this, so that when you take the limit of these weighted discrete operators, you get something that's going to meaningfully define an operator on the entire space SG. So it turns out that the number that you need is exactly 5 to the power m. There are reasons to sort of see why this is the case, but I'm just not going to focus on this today. I'm just going to focus on the fact that if you take this weighted limit, except for this constant that you can sort of remove, it's not very important. The limit of this is going to define an operator on the entire gasket, and that operator is what we're going to call our Sierpinski gasket. Oh, sorry, our Laplacian on the Sierpinski gasket. So another talk for this will be sort of to talk just about the Laplacian on the Sierpinski gasket. It turned out that it's depending, the way I define it here is going to be a non-positive operator. It's going to have like a discrete spectrum, and it's going to sort of give you a set of orthonormal basis of eigenvector, especially if you sort of put like a Dirichlet boundary condition. And using that, okay, I think I missed, this is a typo. Using that, I can write a green function for this Laplacian, and it's going to be given by the sum of lambda k to a negative 1 phi k sk, where lambda k are the eigen values of the Laplacian, and phi k the corresponding orthonormal basis of eigenvector. All right. So we have our Laplacian. Another thing you can define the notion of derivative. So there are two kinds of derivative that are important here. So the derivative are going to be defined at the boundary of my Sierpinski gasket of my fractal. So the boundary, I'm going to sort of consider boundary quote unquote to be this 3.q0, q1, and q2. And so there is a notion of normal derivative, and there is a notion of tangential derivative. All that to sort of say that if you sort of piece all these things together, you can have an equivalence of the Green-Gauss formula that sort of say that if I take the integral over the Sierpinski gasket of u multiplied by the Laplacian of v, and then take away the minus v Laplacian of u, if I integrate this, then I'm just going to sort of be dealing with boundary value here. The value of u at the boundary and the value of the normal derivative of u of v at the boundary, and vice versa. So this is a valid like formula. There are many things that I haven't said. What's the domain of the Laplacian? I will sort of put all those under the rug for now. Suffice to say that functions in the domain of the Laplacian are going to be continuous on the Sierpinski gasket, and they're actually going to be smooth. So we're going to, especially we consider only smooth function for our case. So polynomial will sort of be those kind of functions. What else? There's one thing I did not define, but I think I should have, so I'm going to quickly mention it. There's a measure here that I put here. So that's actually something important. So why don't I sort of add like a quick page to sort of describe this? So what I want to sort of do is that, okay, I want to define a measure, a probability measure on this, and the probability measure is going to obey exactly the self-similar equation that I sort of set out to sort of satisfy. So what does it mean? It means I'm going to define the measure mu. That's going to be a probability measure that will assign weight 1/3 here, 1/3 here, and 1/3 here. And then when I repeat this process, if I were to divide this again into 3 parts, then this is going to be 1/9, 1/9, 1/9, and so forth. So in other words, if the mu will be a probability measure, on SG, such that for any word omega of length m, if I look at the measure mu of f omega of SG, it's just going to be 3 to the power minus m. Okay, and they are exactly 3 to the power m such set. So if you add all of them, you get like exactly that the measure of the Sierpinski gasket is going to be 1. So that the probability measure, that the measure that are going to be considered in this talk. So when I look at L2 of SG, I mean L2 of ST with respect to this probability measure mu. All right. So I define the gain function here. So I have a correct value here. So you can solve a Dirichlet problem here, which is actually what interests us because we'll be looking for like a sort of multi-harmonic function. So the solution to the Dirichlet problem is given in terms of a gain function. And the gain function, as I sort of mentioned earlier, is given by this formula. All right, so at this point, I've sort of summarized very quickly what could have been like a different talk by talking about the Laplacian on the Sierpinski gasket. I introduced the notion of a gain function. I introduced the notion of normal derivative. And I'm about now to sort of define what a polynomial on this set is going to be. So I want to sort of just take a quick minute to sort of pause here. If you have any question, you can ask me now, or I can just continue. So let me know if you have any question. Otherwise, I'll just continue.
Yeah, I do have a question because in this function G that you have there, so those files you said they were like agent vectors, right?
Yes. So the phi, okay, if I were to write, what you have is if you look at the Laplacian of phi k, they're going to give you lambda k phi k. And I mean, if you're looking at only like Dirichlet condition, then lambda 1 will be less or equal to lambda 2. So we're going to only accumulate to plus infinity.
Yeah, but they are not. I mean, they are not polynomials, right? In general, they're
Oh no
just functions.
In
right?
fact, yes. In fact, when I say polynomial, you're going to see that I'm making a big abuse of language, because it's not going to be a polynomial in the classical sense.
Yeah.
So these functions are not my polynomial yet. They're not polynomial.
Okay. Because that expression looks it's very similar to one expression that we have in the theory of orthogonal polynomials, which is the reproducing kernel.
Yes, but you can have a reproducing kernel formula. I can talk about it later, but this is actually, think about like the classical, solving this equation on the unit interval, second derivative of x is equal to lambda f of x. And under the boundary condition that you have f of 0 to be equal to f of 1 to be equal to 0. So this will give you like this, the cosine Fourier series, the sine Fourier series, I believe. And you can think about this function as some sort of harmonic, sort of not harmonic, but some sort of function that look like your sine and cosine function on the unit interval. They are not polynomial. They are just eigenfunction of the Laplacian.
All right. Okay. Thank you.
Any other questions? All right. So now I want to define a polynomial, and this is where it might sort of make sense to pause for a minute, but maybe I'll do everything together. So a polynomial on the Sierpinski gasket is going to be a solution. So if I fix a degree j greater or equal to 0, a polynomial will be a solution to the equation Laplacian to a power j plus 1 is equal to 0. And why is that sort of a good definition? Maybe I should add like another page to sort of show you why this is actually like something that makes sense. So let's just consider like a polynomial on the unit interval. Let's take 0, 1, and let's look at p of x is equal to an s to the power n plus all the way to a0. All right, we know what a polynomial is, just a combination of monomial, but you can sort of agree with me that if I look at Laplacian here to be the second derivative, d over dx squared, then there exists a power sort of L, a number L, which is an integer, so that if I sort of apply the Laplacian, let's say L time to this function p of x, I'm going to get equal to 0. In fact, I know exactly what this is going to be, because if I only sort of take like n plus 1 derivative of this polynomial, I'm going to get 0. But the point that I was trying to sort of make on the factor is we don't have a notion of first derivative. We don't have any of that notion. We were able to define an operator that acts as a Laplacian directly. And so in analogy to this, I'm going to just declare something to be a polynomial of a given degree anything that's a solution to Laplacian to a power j plus 1 equal to 0. So in particular, for j equal to 0, Laplacian of u equal to 0, it's going to be exactly harmonic function. Harmonic function. And then for j equal to 1, you're looking at Laplacian square of u is equal to 0. This have a biharmonic function, or the analog of the biharmonic functions. And so in general, when j is greater or equal to 2, I'm going to look at Laplacian j plus 1 of u. I'm going to say equal to 0. This will sort of lead to u is going to be called a polynomial. A polynomial of degree j. If you really want to be precise, I mean, if we're going to stick to sort of a notion from classical harmonic analysis, u is in fact a multi-harmonic function, a multi-harmonic function, meaning that some power of the Laplacian will annihilate like this function u. And so this is what I'm going to call for the rest of the talk a polynomial. And it does sort of make a little bit sense if I compare it to the classical case, because for any polynomial, I can find a power of a Laplacian, a power of a second derivative that's going to make it exactly equal to 0. In particular, if I were just to look at the unit interval, and this is worth maybe highlighting, if I look at d2f of dx squared equal to 0, then this is f of s is equal to ax plus b. This is exactly an harmonic function on your unit interval. So this analogy seems to sort of be like a good one to sort of make in this particular case. So I want to sort of make sure that we all agree on the definition, because this is what I'm going to call a polynomial going forward. And you can clearly see that an eigenfunction will never be a polynomial, because an eigenfunction is just like, I mean, if you take like lambda, the Laplacian of phi k, you just get lambda k, or minus Laplacian, you just like lambda k. So in particular, the function that I have is in this expression are not going to be polynomial. All right, so if you agree with me, then I actually put this definition, I put a lot of things together. You can actually sort of, I mean, I could prove this differently, that in fact, this is a finite dimensional subspace, and the dimension of this space is going to be equal to exactly 3 times j plus 1, but I just sort of include this in the definition. I'm going to sort of maybe convince you that for harmonic function, all you care about, as in the on the Euclidean space or on the unit interval, to define an harmonic function, I just need to tell you the value a, b, c at the boundary. If I give you those values at the boundary, there is a very simple algorithm to sort of tell you what the value at any of the next point are going to be. And because harmonic functions are going to sort of be continuous by definition on this case, we can just extend them uniquely. So we have a pretty simple algorithm to sort of compute the value of an harmonic function at any point on the Sierpinski gasket. And harmonic functions are defined exactly by their boundary value. So if I look at h0, the dimension of h0 is going to be 3. And then if I look at h1, then I also need to sort of impose like a bound condition on the derivative. So that's why you sort of get 3 times j plus 1 in general. So for the biharmonic function, the dimension of the space will be 6. And then for the triharmonic function, the dimension is going to be 9, and so forth. Okay. All right. So we have a space of harmonic function, a polynomial here. One thing that I want to sort of maybe highlight here as some big difference between classical theory of polynomial. If I look at the closed linear span of all the monomial that we just defined, like take all the polynomial, let's not call them monomial. Let's take all the polynomial that we just defined, take the closed linear span in L2 of mu. Then you can actually prove that the orthogonal complement of this is not equal to 0. In other words, polynomials are not dense in this sense. So in particular, the analog of the Weierstrass approximation theorem is false. You cannot approximate like a function by a polynomial on the Sierpinski cascade. So there is something that in the orthogonal complement of the polynomial here. Something also that's worth pointing out, if you give me any non-constant function in the domain of a Laplacian and polynomial are in the domain of a Laplacian and they are not constant. If I take u to the power 2 and multiply u by itself, then this new function is not even in the domain of a Laplacian. So it has no chance to be a polynomial again. So one outshot of this is that the space of the domain of a Laplacian on the Sierpinski gasket is not an algebra. So multiplication is not a good operation here. So if you go back to the way we define, we put the three-term recursion formula in the classical case. If you remember, what we've done is we took one of the orthogonal polynomial, multiplied by t to raise the power to by 1. We cannot do that here. We cannot multiply. There is no notion of multiplication. So we need to find a different way to actually increase degree of polynomial here. And it's very natural to sort of see what that has to be. It has to be an integration against the green function. So if you give me a polynomial of a given degree, if I integrate that against the green function, then I'm going to get a polynomial of degree one more than what I started from. And this is going to be the main operation that we're going to sort of be using going forward. So I've defined the notion of polynomial. I've defined the space of polynomial of a given degree. It's a finite vector space of dimension 3 times j plus 1. I've sort of told you that the set of polynomial, if I sort of take them, I look at the closed linear span, is not dense. The Weierstrass approximation theorem is not going to hold. Multiplication is not allowed in the domain of a Laplacian here. So in particular, I cannot multiply two of these polynomials to get a polynomial of higher order. The way to get a polynomial of higher order is actually to integrate against the green function. And we have to keep doing this over and over again. So having defined all of those terms now, I want to show you some function on the Sierpinski gasket. So I'm going to give you an example of a basis of polynomial. And this basis is going to look like the monomial that we know on the unit interval, for instance. So the basis is going to be defined as follows. So the first thing is I'm going to sort of choose one of the three boundary points that I sort of told you about. So I'm going to fix one of the three boundary points. For the remaining of the torque, I'll probably fix n to be equal to 0, and I'll do everything with respect to the boundary Q0. So I could have done that without sort of bothering you, but I want to show you that there is a flexibility in the construction that is to come. So if I let j to be any non-negative integer, then the basis for the space of polynomial of degree g consists of function of this type. They're going to be called p, k, I, n. I can take like only value 1, 2, and 3. It's going to sort of tell us something about like whether or not the polynomial that we're looking at is symmetric or anti-symmetric. I'll sort of show you this in a picture. And then the value k is going to go from 0 to 1. So if you sort of take this into account, you're going to have j plus 1. And then because you have that for each of the I, that's going to give you exactly 3 times j plus 1 function, which is exactly the basis that you're looking for. Keep in mind that I fix a boundary point, so it's going to be with respect to a given boundary. And the polynomial are going to satisfy this equation. So when n is equal to 0, I'm going to remove a subscript. I'm going to go forward writing like string of the form pjk. So when you sort of see starting from the next slide, you're going to see that I'm only going to sort of write this because I'm going to fix the boundary to be equal to n equal to 0. A few things about this. If you take the Laplacian of one of these monomial, you get exactly the monomial of 1 degree less, right? So the Laplacian will sort of kill one degree of your polynomial. That's all the Laplacian is going to do. When the parameter I, which can only take value in 1, 2, 3. When I is 1 or 2, then the polynomial Pijn are going to be symmetric. I'll show you a picture in a minute. They're going to be the analog of the the even monomial on the unit interval or on the interval -1 to 1. And when I is equal to 3, then Pj3 is going to be the equivalent of the anti-symmetric monomial. So essentially the equivalent of the analog of order degree monomial function, okay? And in general, you can write the entire space of a closed linear span on polynomial. You can write as a direct sum of the one that are symmetric and the one that are anti-symmetric. For the remaining part of the talk, I'm going to focus on the anti-symmetric part. and because it's a little bit easier to describe, okay? And when I call HAS, I just mean the closed linear span of the anti-symmetric polynomial. So these are some picture of this polynomial. Maybe I'll make this a little bit bigger. Yep.
I have a question. Is when you say symmetric, is under reflection around
exactly. So
I3?
Exactly. So the picture is going to actually help you to sort of see what I meant by symmetry. So this is a picture of one of the polynomials. So the first one, this one, is a P3, 1. I said when it's 1 or 2 is symmetric. What do I mean is symmetric? Okay, I fix the boundary to be Q0. And then, so, okay, maybe I should say a little bit about how this picture are drawn. So the way we draw this picture is the following. We look at in 3 dimensions. We put the Sierpinski gasket itself on the XY plane. And then at each point on the Sierpinski gasket, we just draw the height of the function. That's what you're looking at over here. So the bottom here is just the XY plane. We draw the Sierpinski gasket there, and at each point of the Sierpinski gasket, we just evaluate the function. So we just show the height of the function. And so this is the boundary Q1, this is the boundary Q2. And when I say the function is symmetric, in this case, I said it's just an even function. It's symmetric with respect to the line that goes from Q0 to the midpoint between Q1 and Q2. Is that answer your question?
Yes, here you're assuming n equals 3, right? It's around.
No, so the factor n can only take values 0, 1, or 2. So here I take n to be equal to 0. So I'm making everything symmetric with respect to the boundary point Q0. So if I were to label this graph, this is Q0, this is Q1, this is Q2, and so forth.
Yes.
Okay, so the picture that you have here, this is P31, these are symmetric. This is a P51, so this is a degree 5 polynomial, that's symmetric. This is a P22, this is a 2-degree polynomial, that's symmetric. And I'm going to show these last two are anti-symmetric. You can see that they're sort of anti-symmetric with respect to this line. So this is Q0 again, Q1, and then Q2.
Okay, thank you.
Okay. All right. So now that we have a polynomial, we can talk about like orthogonal polynomial. But I want to tell you that, I mean, the thing that I just described to you, I show it to you on the Sierpinski gasket, but you can actually do it on any fractal that's sort of self-similar and satisfy some mild condition. Usually these are called PCF fractal, PCF, and PCF stands for post critically finite fractal. So this just tells me that my fractals are barely connected. In the case of a Sierpinski gasket, they are connected but barely because I can just disconnect them by remove any of the point that I use in the graph approximation. So here I don't want to delve into this. This is another fractal. And this one, the graph, I just show the graph approximation. So this is the graph G1 and this is the graph G2. The way to think about this is that the way to go from G1 to G2 is that I'm going to add 2 boundary points. I'm going to add 3 edge, and then I'll repeat. So if I were to go next time, I'm going to add 2 boundary points here, 2 new vertices here, and I'm going to add 3 edge. I'm going to do the same here. I'm going to add 2 points, and then I'm going to add like a 3 edge here. I'll do the same here. I'll do the same here. When you do this infinitely many times, you're going to get to a set. It's going to be a compact set. You can define a probability measure on here, and then you can sort of define like a Laplacian, look at the property of the Laplacian. When you do that, you get like what's called the bubble diamond fractal, and these are sort of polynomial on this set. When b is equal to 1, this is just a unit interval. So if you were to do this, you'll just get the Legendre polynomial again. But when b is equal to 2 or higher, you get things that are different. So I'm showing here just like harmonic function on this set. The bottom line is what I'm just sort of talking about is valid for a large class of fractal, not just the Sierpinski gasket. But for the remaining of the talk, I think I'll just sort of stick to the Sierpinski gasket. I think I'm getting close to what time should I stop? Because then I can speed up or.
You still got like
17 minutes.
17 minutes, great, okay. So now you can introduce a Legendre polynomial any way you want, but for me, and from what I said before, I like to look at it as optimizing, sort of minimizing or finding the best approximation to a given function in L2 with respect to polynomial. So, easiest way to do it is just to sort of apply Gram-Schmidt to the monomial that we just defined. So that's what I'm going to do. I'm going to fix, we'll do everything for n equal to 0 from now on. And I'm going to apply the Gram-Schmidt orthogonalization process to the monomial pjk that we constructed. We're going to get a new set of orthogonal polynomial now, and I'm going to denote them small pjk. So small pjk are the orthogonal polynomial that are obtained from the monomial that I just described on the last page. And then when I normalize them, I'm going to call that family QJK, and QJK are just going to sort of be like the orthonormal polynomial that we just sort of characterized. So this is the same thing. Many of the pictures that I'm going to show them for the anti-symmetric one. So I'm going to take only I equal to 3. So for that, I'm just going to remove the dependence on K here. I'm not going to worry about that anymore. So whenever you see like Q and with just one index, then it's just going to be like the anti-symmetric. So those are the ones that I might sort of focus on. And in particular, they form an orthonormal basis for the closed linear span of the anti-symmetric polynomial in L2, okay? It's not surprising that you can actually write this in a determinate form. So with proper normalization, if you write the determinant of the inner product between the monomial and you expand it out, you get exactly your orthogonal polynomial. So there is a good set of analogy between this and the classical theory in terms of how they are obtained. Now, the first big difference, which is also not a big difference because we end up exactly at the same place, is that if I take the orthogonal polynomial or the orthonormal polynomial, whichever you want, if you take them, you're going to show that they satisfy a three-term recursion formula. But it's a very special three-term recursion formula. So this is a function that I call fk plus 1. That's going to be an auxiliary function. And that function is exactly what you get by sort of integrating a polynomial, one of these guys. You integrate it against the green function. You're going to get a polynomial of degree k plus 1. And if you try to expand that into the orthonormal basis, you're going to get exactly a three-term recursion formula. Why is this sort of natural? So in the classical case, when you have your pi k of t, what you do is you take t multiplied by that. That gives you a polynomial of degree k plus 1. And the expression of this is what gives you the three-term recursion formula. I mentioned earlier that we don't have a multiplication operator on the Sierpinski gasket, so we need to do something different. So this is what replaces our multiplication operator, is the green operator essentially that sort of allows us to increase the degree of polynomial. And so if you look at that analogy, then this formula is not sort of far-fetched, and in fact, the proof is not that difficult. All you have to do is to look at the inner product of this new function, fk plus 1, and your monomial function, your member of your orthogonal family. You can sort of prove that. You can change it to like fj plus 1, where fj is just like the same thing, but with j, inner product the qk. And if you were to expand it, you can show that, okay, whenever j plus 1 is less than k, if you were to expand this as a family of polynomial, then this is going to sort of be written in terms of things that are going to be all orthogonal to qk. So from there, you notice right away that all the inner product are going to be 0 whenever j is less than k minus 1. So you only are left with the term that corresponds to k plus 1, the term that corresponds to k, and the term that corresponds to k minus 1. And then you sort of try to figure out those terms, and that's how you end up with this three-term recursion formula. So we have our three-term recursion formula. One thing we can do the similar statement for the symmetric orthogonal polynomial. I will probably not sort of worry about this too much now. So it's just Gram-Schmidt for a different family. And I'm not sure if you notice what's going on here. So maybe I should sort of highlight why I included this slide, but I'm not going to sort of talk about it too much. So I know my space of polynomial. I can break it into a direct sum of the symmetric and the anti-symmetric. Now, I apply Gram-Schmidt to this. I apply Gram-Schmidt to this, and then I combine it. Automatically, they're going to be perpendicular to each other, and I'm going to get an orthonormal basis for this space. However, there are two families in here. There is a family that corresponds to, so this was called P, big P, J, and then I call it I, and I can be 1 or 2. There are two families. These two families are not orthogonal to each other, so I cannot just sort of, applying Gram-Schmidt here is going to be a little bit trickier. That's why I sort of decided just to show you what happened on this space, because there is only a single family here. Now, what I've done here, out of this family, I pull one function out. That's one family of function that's going to sort of be completely symmetric, and I apply Gram-Schmidt to that. So this is still giving me an orthonormal basis, but it's not giving me an orthonormal basis of the entire family. So there is something that I have to do in order to correct that, and that's what these two results are saying. But the bottom line is these are sort of technical detail. I'll just sort of maybe focus on what happened on the anti-symmetric set, because it illustrates essentially the entire theory. But if you want to sort of, in full disclosure, I can actually get an orthonormal basis on polynomial, and this is what I have at the bottom here. But I will not sort of give any detail on these ones. So maybe before I go forward, I'll show you some of the pictures. So these are some of the pictures of some of the polynomials. So this is anti-symmetric. The Q are all anti-symmetric. The S are symmetric. And then the phi are sort of a combination. So the combination of symmetric and anti-symmetric. Some of them will be one of the two. All right, before we go forward, I want to sort of maybe trick your eyes a little bit. So I took one of these orthogonal polynomial, and I look at what happened on the restriction on the interval. So you remember what the way I sketched the picture was, I draw the Sierpinski gasket on the XY plane, and then at each of these points, I just draw the height of the function. Now, what I'm going to show you is I restrict everything to the line Q0 to Q1. So this is Q0, and this is Q1. I restrict my function here and see what happened on that single line. So this is what you're looking at here. If I look at the Q0, it seemed to the eye that this is just a straight line. And this seemed to sort of be like maybe a third-degree polynomial. This seemed to be maybe a fifth-degree polynomial, the way they look like. And the symmetric one, this seemed to just be like a flat function 1. This seemed to me be like something like a double parabola, like s to the power 4, and so forth. So when we first saw this picture, we thought this thing, the restriction looked really like polynomial in the traditional sense. But there is a very nice result that says that if I restrict any of these functions, any polynomial, if I restrict them on the line Q0 to Q1, which is nothing but the line 0, 1, the function is not actually differentiable at any of the point that constitute like the point in the graph that we use to approximate our Sierpinski gasket. And in fact, at any such point, you can prove that this function will have infinite slope at any of these points. So it's not just that they're not differentiable, they're pretty bad. So this picture, they look like polynomial, they look like line, but they're actually far from being like a smooth function. Other thing that you can try to sort of do here, you can look at the nodal set. So the nodal set are the set where this polynomial are 0, or the point where they are positive and negative. And what you're sort of seeing here is like I draw in sort of gray the place where the function has positive value, and where you have all white. Okay, this all white was just they did not belong to the interval, but any other place that's sort of white on this area, those are the place where this function Q1 is negative. And so we were able to sort of trace out some of the 0, at least numerically, where this polynomial is 0. So you have 0 along this line, but you have over 0 somewhere along here. And so the set that you're looking at here, wherever you see something, it's where the function is positive. Where you don't see anything is where the function is negative, and the boundary of the two is what we are trying to capture. And those are called the nodal set of the polynomial. We have a lot of numeric about this, but we can't prove anything about them. We don't know how the D0 are distributed, for instance. This is a similar thing for the bubble diamond. So if that I showed you earlier, if I do it for b equal to 1, I capture exactly again the Legendre polynomial. But if I sort of take like the branching parameter, that b parameter there, if I take it to be 2, I have some very sort of nice looking like polynomial, but orthogonal polynomial. But I will not sort of spend time on that. So what I would like to maybe take a few more minutes to talk about is the three-term recursion formula. So we know we have a three-term recursion formula, so we can get like a Jacobi matrix. And I want to analyze that Jacobi matrix. The first thing to get is that the Jacobi matrix is actually a bounded operator on L2 of a natural number. And I know exactly what the bounds are because the coefficients that appear here in this matrix here, these coefficients are bounded by the L2 norm of the green function. And I can estimate the L2 norm of the green function. We have numerical estimate that shows that this is bounded by something like of the order of 0.129, I think, something like that. Okay, so we have estimate of this thing. And from there, if you sort of go to the classical theory of Jacobi matrix, then you can associate to this Jacobi matrix a spectral measure, mu of S, and the spectral measure will be supported on this interval. And that spectral measure will have like a three-term recursion formula that corresponds to exactly what you should have sort of obtained in the classical case. So what we've done here, we start from polynomial on fractal, polynomial on SG. And then what we've done, we sort of created polynomial on an interval minus alpha to alpha. Okay, so multiplication is not defined here, is not defined, but multiplication is defined here, is defined here. So what we're trying to do is actually trying to capture a way to actually interpret the green function that we defined here. We want to sort of state the green function in terms of this multiplication operator that we get using the spectral theory of this Jacobi matrix. And before we go further, the polynomial, the orthogonal polynomial, classical, these are classical polynomial. So meaning when I mean classical here, I mean they are defined on an interval of a 4 minus alpha to alpha. This is function on the real line. So the one that corresponds to the one that I just described are these sort of pictures. We can do some of these pictures quite to some precision, but the numeric gets sort of tricky and then things get sort of very unstable. So I sort of sketch a few of them here. This is for the anti-symmetric polynomial. If I start from anti-symmetric polynomial on the Sierpinski gasket, this is what I get. And if I start from the symmetric polynomial on the Sierpinski gasket, these are the one that I obtain. They are two different families, actually. So what I want to maybe sort of end with is how you sort of get a multiplication on the Sierpinski gasket. So what we'll do is we'll define a unitary map U that's going to sort of go from L2 on the integer to L2 of the spectral measure. And the multiplication of this map is just going to intertwine like the mapping T, okay? Where T is a natural multiplication operator on V space. Now, on the other hand, what I can do is I can define the green operator. The green operator can be defined on the Sierpinski gasket or L2 on the Sierpinski gasket. And what I'll do is I'll define an operator that will take a function on L2 of the natural number to L2 on the Sierpinski gasket, and to any sequence is just going to sort of give me like the expansion into this orthonormal basis. And it turns out that the map J here and the map J here are exactly the same. So if I were to write this correctly, it's sort of saying that certain diagram of operator is commutative. That's all I'm sort of trying to say. So this allows me to sort of see how I can do this operator, which is a multiplication operator on a real line, how I can sort of identify it with the green function or the green operator on the Sierpinski gasket. So as a result, we're able to actually identify exactly what this space the space of orthogonal polynomial of that are anti-symmetric on the Sierpinski gasket, we can identify that space with L2 of on this interval with respect to this measure. So this part is still like something that we sort of trying to clean up to sort of publish, but these are some of the main results that we obtained so far. And I mean, maybe to stop, I can sort of introduce the Sobolev legend of orthogonal polynomial. The main difference is that you use a different inner product, and the inner product depends on the parameter lambda. In the classical case, there are many difficulties in dealing with this because you don't have the integration by part anymore. There is no more three-term recursion formula. But we can essentially do almost everything that can sort of be done in the classical case. And rather than sort of showing you specific result, I might just show you some of the picture. Now, you can notice that from here to here, these are very noisy. And most of the computation that we've done so far, and they are maybe at least 4 years old now, they tend to sort of contain a lot of errors. So some of the things that I'm hoping to do this summer with some of the students is to refine this computation so that we can sort of get rid of some of the error that we see here. So the point of this last slide is to say that we can define the analog of a Sobolev orthogonal polynomial on the Sierpinski gasket, and by Sobolev I mean something that's sort of going to be orthogonal with respect to an inner product of this form. We can analyze what happened with respect to the parameter lambda. When lambda is equal to 1, this is exactly almost a Sobolev space, but when lambda is bigger than 1, this is slightly a generalization. So with that, I think this is a good place to maybe stop and maybe take more questions and have some discussion. If you want to read a little bit more about analysis on fractal in general, the part that I didn't talk about, this is a very nice book that sort of introduces analysis on the Sierpinski gasket. And if you want to look at it on general fractal, that the PCF that I mentioned, this is a book by Kigami. The first paper about polynomial or orthogonal polynomial on the Sierpinski gasket is the one that I mentioned earlier. This one describes, this one right here describes the Sobolev orthogonal polynomial on the Sierpinski gasket. And this part is something that sort of in the work is not finished yet. And the thing that I mentioned about the bubble diamond fractal, which is another class of fractal for which we feel it can be sort of developed, is in a paper that we just put on the archive, and it's probably going to be submitted very soon. And with that, I'd like to thank you and maybe take more questions from you. Thank you.
Okay. Thank you, Kasso. Is there any questions?
Yes, I do have questions.
Okay, go ahead.
Thank you, Kasso, for your talk. Is there anything analog for general PCF fractals of symmetry and antisymmetry? Because I guess this can be extended to nested fractals, but what about general PCF fractals?
I think it's extendable. The reason we didn't sort of do it exactly is that we don't have that much numeric on the generic PCF fractal. But otherwise, you'll have some trouble in defining the part that are symmetric or anti-symmetric. That might not sort of be like easy to do. But in generic term, we exploit the symmetry and the anti-symmetry to actually define bases that are easy to work with so that we can see numeric. But otherwise, I could have defined like a polynomial of degree j to be a solution to Laplacian to a power j plus 1 equal to 0. I could sort of go ahead to define what it means to be like orthogonal polynomial with respect to the measure, the probability measure that come with my L2 on my fractal. So the theory is still going to work. You might not be able to actually sort of get a good numeric. But and also the fact that I use symmetry and anti-symmetry simplify a lot the way I actually construct the basis in the end. And I didn't sort of show what happened on the symmetric part because the symmetric part is a little bit messy because since the two parts are not orthogonal, I have to sort of put a good order into this space in order to sort of keep track of what the Gram-Schmidt process is doing. So we got around that by sort of taking one subfamily that completely symmetry, by sort of grouping everything so that essentially you have full symmetry. And then we sort of orthogonalize that part. So we still actually don't know fully how to actually sketch a graph of a polynomial that's going to be in the symmetric part by itself. I only know a sub part of that.
Okay.
Okay.
Is there any knowledge on the complement in L2 of the monomials?
Oh yes, so that's part of a paper that we're preparing now. So it's going to be the set of the space of localized eigenfunctions. So that's what they're going to be. So we almost sort of close to finishing that paper.
Oh, cool. And the last question, you draw the zero set on some of the polynomials. Is that always totally disconnected, or?
I actually don't know anything about this. So I don't know. I don't know if many of you know Bob Strickers. So Strickers used to run this so-called REU, research experience for undergraduate, where they come and they do research, and then we get some numeric, and then we write paper. So this picture that I just showed you, this picture is from maybe more than 10 years ago. And since then, we try, when he was still alive, we tried to describe a little bit more this zero set, but we couldn't say anything about it. What you see there is just what I know. They look completely disconnected, but I cannot prove it. And also what you see there is probably misleading a little bit because the numeric is not that good. Like think about like 10 years ago. I mean, this was written in MATLAB, and then, so maybe by redoing this, we can sort of get a better sense. We can go to high degree polynomial and maybe get a better sense of this zero set. And this summer, I'm running a project with students. So my hope is actually to get more numeric to maybe answer some of these questions.
Thank you.
Any other questions? I have a couple. In your definition of Sobolev orthogonal polynomials, I noticed that there's two parts in the integral, ones with the Laplacian and the other which is just the polynomials. And I noticed that you have the same measure in both integrals. Is that a requirement? Because normally, at least in the theory of orthogonal polynomials, you can have like different measures.
That's a good point. No, so no, there's a lot of way you can generalize what I'm saying, and excuse me. The only way we know how to do it, because many of these things started from a numerical side, is that we know how to deal very well with this probability measure. Okay. But you're completely right. You could put two different measures and then see what happens.
Yeah, and there's another question related to that we call that kind of Sobolev polynomials as continuous Sobolev polynomials, in the sense that the part of the Laplacian is an integral, but you can for instance the other measure, that measure could be like a discrete measure, and you could have like a Dirac delta, for instance, and we call that discrete Sobolev polynomial. So I think that's also possible here. Do you see this?
Absolutely. Yes. So it was a list of things that we hope we could do, but I never got a chance to actually do it. So if anyone wants to look into this thing, I mean, you're welcome. Yes, definitely. There's this review paper by, I don't know, he's on, I can say, I think it's Marcellon.
Marcellan, yes.
Exactly. This review paper, in fact, that was the motivation for many of these things. We read his review or his short paper in the notice of the EMS maybe about a couple of years ago. And after we read it, that's when we sort of had the intuition of trying to extend this thing to the Sobolev case. And so there's a lot of variation of what I present here that one can look into. So the discrete part will probably not be too difficult to actually get started, because that one I feel like I think we have all the tools to do it now.
Yeah, I think in the standard polynomials, the discrete case, I think from my point of view at least, is like easier than the continuous case. So I'm not
Yes.
sure if that's the situation in fractals, but probably it could be worth to look at this. Yeah.
I'll be happy to chat with you about this offline if you want to.
Yes, I'm interested in this. And the other question is about this Jacobi matrix, because you know that in the standard case, you can get information about the zeros of the polynomials.
Yes.
I'm not sure in this case because you have something different here, but have you
Yeah.
looked at that?
No, because okay, that's a good point. In fact, the reason I personally start looking at the Jacobi was actually to try to get something about the zero, but all you can get is you can get zero of a polynomial that you describe on the real line. So
Yeah.
I feel somehow like this Jacobi matrix just give me some way to identify the end. I mean, from my point of view, what this Jacobi matrix allow me to do in the end is to identify the space of polynomial and the orthogonal complement. That's what this allow me to do, because I can sort of translate that into an exactly L2 space with a given measure on the real line. And that's what this allow me to do. But originally, it was to sort of understand the zero, but there is no connection. I couldn't see any connection.
Yeah, so there's probably another operator, not that integral maybe, that gives you that, but I'm not sure. I'm not sure anything.
Oh, I see what you're saying.
That's probably that's not the correct operator, maybe, because basically what you're doing is you're replacing the multiplication by x by this integral with respect to g, right?
Yes.
But probably there's another one. I don't know, but
that's a good point of view. I don't know. That's
yeah.
a good point of view.
Yeah. Okay.
I'll be happy to chat offline, definitely, because this is I ran this project this summer, and I have some questions, and so there'll be enough people to work on this for maybe the next 6 or 7 months. So if you want to chat online, I'll be very happy to.
I'll be happy too, because this is very interesting. Yeah. Yeah, well, I think I can probably contact you later on, and we can discuss.
Absolutely, that will be great. I'll be very happy to do that.
All right. Any other questions? Okay, if not, okay. Well, thank you very much, Kasso, for a very nice presentation.
Thank you so much for your invitation. I'm very happy.
We can probably discuss. I will contact you later to discuss this.
Okay.
All
Thank
right.
you, and happy holiday season.
Yeah, you too.
Bye.
Thank you, all of you. Bye-bye.